shorter than an hour per task. And so how do you so can you see my screen? I hope so.
Yes.
Okay. And how you submit your homework. So in there, this is my student ID. Same as you. So go to there. You are assigned. Then from there, then you can upload your file in here. Let me try. PPE. Copying this. First name, last name, SBUID, which is not correct, and PP1_1. Okay, then you're gonna keep sending 3 of those, then turn in. This is how you submit your homework. Okay. Then from there, we're turned in. Then I'm able to see the time you click it. Then if you submit late, the 1 minute late is also, let's say 5 minutes late is 1 day late. But don't submit it late. Then TA will give you a score. Clear? Okay, so I know most of you completed your homework. And let's talk about the one homework. 373 PP2 maybe. Okay, so PP1 first. So how do you solve this problem? So you understand the test number 1 and 1, right? So your job is you are a robot, and your robot can able to up and down and left and right. So initially there is a robot on position 0 and 0. The given sequence it moved judges if the robot makes a circle, which means it moved back to the original place, which means 0 to 0. The move sequence is represented as a string, and each move is represented by a character. The valid movement is right, left, up and down. It should be true or false, representing whether the robot makes a circle, meaning it's returning to the original point. How do you solve this? So I gave you the line. So, okay, so here is my solution. So I made a 1 counter. So I name it count. And I count all the moves. Moves is my input, right? Then here I count my left and I count my right. If they are same, meaning they are returning to the same point, and left and right. On the right side, up and down, up and down. If they are equal, meaning they are returning. So if they all 0, if they all true and true and true, if it is same, it will return true. And this is also return true if it is true. Then it will return true, meaning let's run it. Right, so then I can play with this. If I have down, down, then it should return false. Okay, clear. If I do up, up again, then it will return true. Okay, this is how you solve the question, solve the problem. Your own way, you can solve it in your own way. You make a longer line, it is fine. But if your answer is longer than a page, meaning you need to think about it again. Okay, so this is how you solve it. And problem number 2, you can solve it by yourself. Number 3 is also. Okay, any question about the how to submit homework and how you finish your homework and how do you deal with the program practice. Any question? No? Okay.
Oh, one more, like a small question.
Go ahead.
So for the task 1-1, my, like, the time clock shows 0.0.
That is fine.
Oh, okay.
First,
So
I have
you
a
can make
question.
it longer if you want to test it longer. Yeah, mine also shows 0.0. Don't worry.
First, like I have a question. Like I did the same way as you did, but when I wrote like collection.counter, it's showing me wrong. It's like collections not identified something. And when I just remove collection part and just counter, it's working for me.
Okay. So you mean without collections?
Yeah.
Without collections, is it really working?
I don't know, but for me, if I put collections, it's not working.
Without collections, it shouldn't working, right?
Yeah, I also thought so, but
We'll see. Okay. Anything else?
Professor, I have a quick question. For task number 1, you put your algorithm with from random import randint and shuffle. Are we supposed to use it?
No. I think it is working without this.
Professor, what if I did not use collections?
Don't worry, your own way.
Yeah.
If you have the same answer with me, that is a problem.
but my answer was the same as exactly same as yours, but I did it earlier myself. Is it fine?
Okay, we'll see. Okay. Then, anything else? Maybe it is too obvious. Any other question? Nope. Okay, so today.
I have a quick question.
Yep.
If you don't mention on the problem that about time complexity or space complexity, we are allowed to have like ON square or just ON or O1. Doesn't matter.
I don't get it. So you mean that your approach is too complex to finish on time? Is that what you're saying?
No. If you didn't mention about the time complexity or space complexity on the question, it doesn't matter if we have a time complexity of ON squared or O1.
Yeah, that's up to you. That is like the
Okay.
way of thinking. You're processing and thinking, right?
All right. Thank you.
Okay. So so in our algorithm class, there is no recommended answer. Okay, your own way. So algorithm is not about the following the answer, but about how you're thinking. All right. Okay. Anything else? So let me start my class today. Stop sharing it. Screen, share screen. Multiple people can share this. Okay. So today we're talking about the program analysis. Oh, well, one more thing I want to show you. So this is how I marked your attendance. So we have 28, 27 of us. So whenever you raise your voice or give a comment or question, I marked as 0.5. Okay, and if you did more than 2 times, you're marked as 1. Okay, this is attendance, not physical. You are not just log on, but you are keep asking and you are doing interacting. That's how you get the point. So this score will be maxed at 10 at the end of the semester. Okay, so I highly encourage you to participate in the class and interact with me. Okay, all right, so go back to the point. All right, so today we're going to talk about the program analysis. What is it? So we cover in our program practice in the PP and Python notebook and problem day. Let's think about this. So warm up your brain after the lunch. So for each of the following pair of functions, f of n and g of n, state whether f of n is big O of g of n or f of n is omega of g of n, f of n is big theta of g of n, or none of the above. So let's solve this problem, 1, 2, 3. Okay, let's think about for 2 minutes, then we're gonna discuss about it. All right, so warm up your brain. So everybody come back on it?
I think for number 1.
Yeah, one second. So for everybody, write an answer in the sequence A, B, C, D. So my answer could be E, D, D, something like this, okay, for your response. Okay, so I'm gonna pick the students who are not actively participating so far. So Hey Yuha, what's your answer? Quickly.
I didn't have time to finish them.
Okay, okay.
Can you give me a little bit more time?
Okay, okay. Then PK?
Still need a time, Professor.
Okay, so let's think about 2 more minutes. Suin, what's your answer then?
Sorry for the wrong chat. My answer is
What's your guess?
my guess is BAB.
BAB, okay. So wait for 2 minutes. Therefore, everybody have enough time to think about it. Okay. So I love to have the interactive, and I really emphasize on the interactiveness on the online courses. Without this, I'm just only talking, and you're not able to catch, and you're not able to understand properly in a given time. Ready? Okay, let me pick the Yoon Taeyong.
Oh, yes. Professor,
Yeah,
can you hear me now?
yeah, I can hear you.
Oh, okay, so I got BAC.
BAC. Okay, thank you. Taeyong. Okay, how about Shin Yejin?
I got BAA.
BAA. Okay, let's say Park Subin.
I also got BAA.
Yeah, okay. All right, let's solve the problem. Okay, BAC. So f of n is n squared and g of n 6n plus 7. What does this mean? So whenever we talk about asymptotic is something I really don't want to know detail, but I asymptotically, or roughly saying, okay. So therefore, I don't need to worry about rest of it. I only care about Mazur. I don't need to worry Mazur component, which dominate. And here, I also don't care about this constant C. So I'm comparing n squared and n. Oh, n is definitely a lower bound to the n squared. N squared, n. Therefore, g of n is our boundary. Therefore, it should be B. Clear?
Yep.
Okay, let's go to the second problem. So I don't care about minor, I only care about n squared. Oh, this is n to the power this, right? Therefore, this is bigger, definitely. Therefore, C of n is my upper bound. So there should be my A. Clear? And this one, 2 to the power n and n quad. So who's growing faster? Left or right?
F of n.
F of n grows faster, right? Definitely. Therefore, this is my lower bound. Therefore, it should be B. Clear?
Yep.
Okay, I'm gonna show you, let's say, what was the website? The calculus website?
Desmos.com/calculator.
Desmos calculator. Problem with 2 to the power n. The power n plus n squared plus n squared. And the second one is n quad plus n squared. And okay, right? 2 to the power n squared. 2 to the power n minus n squared. Okay, that is minus. Okay, so red one and blue one. So if you go to deeper, the red one will take it over. Yeah, red one take it over, the blue one. So when we talk about asymptotic notation, we care about the big number. Okay, so 2 to the power n is rapidly, more rapidly growing than the cube. All right, so I have a table for this, then we can talk about it. Okay, so if I show you quickly, this is my table, 2 to the power n and n squared. 2 to the power n is much bigger computation than if you compare it to n squared. Then there is n triple, n quad, and 5th time and 6th time. Okay, 2 to the power n is always greater than something like this. All right, so go back to the point. So now we have a good understanding how do you do big O notation and big omega notation. Okay, so big O multiplication. So none of you have the correct answer, right? BAB. Nobody has a BAB.
I think Suin said BAB.
Oh, Suin says BAB. Okay.
Yeah.
Suin, so BAB. So Suin got 0.5. Does everybody understand? Agree on it? Okay. Thank you, Suin. 0.5. Okay, go back to the point. So big O multiplication by a constant. So multiplication, the constant does not change the asymptotic. Why? Because constant multiplied by constant is still the constant. So big O notation of the f of n inside of f of n, there must be c, right? C, then if you multiply c multiply big C, then it's still c. So we can say, oh, it's still big O of fn. So old constant c become a big O, becomes c multiplied by c, but constant multiply constant is still the constant. Therefore, we don't really care about the constant. And more importantly, when we solve this, we don't care about this following. We only care about dominant. Okay, so big O multiplication by a function. When both functions in a product are increasing, both are important. Let's say, for example, big O of f of n, big O of g of n multiply, then we can say bigger BO, f of n and g of n. Omega and multiply, and we can say omega of it. Okay, big zeta, f of n, g of n, big zeta, f of n. But we cannot use big O, f of n multiply by omega of g of n. This is meaningless. We cannot use this. But we can use big O and big O, okay? And both are increasing, we can use this way. Clear? So this is why running time of two nested loop is 2n squared. So how do you write the nested loop? For I equal 1 to n, for j equal 1 to n. So you loop in through, then you loop in through again. We call the nested loop, and this is n time and n time. Therefore, we can say n squared. All right? So reasoning about the efficiency. So grossly reasoning about the running time of algorithms usually easy given a precise enough written description of the algorithm. But when you really understand the algorithm, this analysis can be done in your brain, in your head. Okay, so you don't need to write down, but in your brain, okay, I ignore the minor factors. I only take up dominant. Then your brain can think of it. Okay, so however you recognize always implicit written algorithm and program, we are reasoning about this. Let's talk about this. So selection sort. I'm sure you know what is a selection sort. Okay, so this is a selection sort. Oh, this is Bober sort, I'm sorry. Selection sort. You have an index on the left. Swap it. Okay, index remained, then swap it. Index updated. Index updated. And swap it to the latest one. This is a selection sort. So what is computation time for this?
N squared.
Okay, good try. Why is it not taking over? Stop sharing it. Okay, we understand what is a selection sort. So we initialize I and j and have a minimum and loop through, pick the minimum, and looping through it, it keep maintain the minimum, okay? Minimum to update that i's position, then maintaining it, like you saw in selection sort. Clear? So worst case, so who said n squared? So everybody says n squared. Why is it saying n squared? Because
Nested loop.
yeah, it is comparing like this, isn't it? When we have so n square is true n square should look like this, like a bubble sort. But this one is somehow different in a selection sort. What do? I maintain the index. Therefore, index in this case is mean value. So this value, and keep comparing it, all the rest of it. If there is a smaller than me, I swap it, right? Then where's my next point? Next point is here. Okay, then from here I'm keep checking it. Then always smallest one come. So smallest one always comes in leftmost, the second smallest, then third smallest. Okay, the second loop is not full search of your values, but it only search proportion to this, because on the left it is already sorted. Okay, I can say the outer loop always run through, outer loop run through all the way from 0 to n minus 1, but in the western loop doesn't search everything, so it comes like this, proportionally smaller. Do you understand what I draw? If you compare to the bubble sort is doing this. Do you understand what I draw in the bubble sort? You know what the bubble sort is, right? I'm assuming you know what the bubble sort is. Then bubble sort does this. It compares everything to everything. But in a selection sort, they do a little smarter than a bubble sort. Which means in a nested loop, in an inner loop, doesn't need to search everybody. Okay, remember this. So worst case analysis, the outer loop goes round n times, okay. Inner loop goes about at most n times. What is at most? For each iteration, doesn't mean it has it going like this, right? There's no computation in there. Okay. The selection sort takes n squared in the worst case. In fact, it is theta. Why? Because half time is scanned through the at least half element. Half time at least. And sometimes rest of half is run through smaller than this guy. Therefore, I can set in the worst case, it goes to n squared. In the best case, it goes very proportional to this. So inner loop only goes about half of it. Are you all agree on the half of it? Half of, why are you saying half of it? Because on average, you are not running through n, but you are running through half of it. Okay, therefore, it could be total list, could be multiplied by this guy, n squared over 2, or in detail, we can talk about 4 to the n squared. Okay, I'm going to talk about this more detail in the following slide. So 2 to the power n squared, this is what we get. And it says total at least of this one, at best of this one. So the most computation comes in here, the smallest computation in here. Then I can say, oh, there is some constant C. There's some constant C. So constant C1 is very close to the 1. Constant C2 is very close to 0 point something, which is not 0, but very close to 0. Therefore, I can set it to constant, which means I can use big theta of n squared. Okay. So more careful analysis. An exact count of number of times if statements executed by this one. Outer loop, inner loop. your computation is 1 times. So you can simplify this portion to n minus I. Then you can as a Taylor series, you can do this by applying 0 to n minus 1. Then sum all of this is 2 to the n multiplied by n plus 1. Okay, therefore it is n squared 2 plus n. So in this case, what we care about, dominant only, and this is my constant.
Professor, wouldn't it be n times n minus 1 over 2?
You mean this? Sorry. Is it correct?
Yeah, I think it's supposed to be subtraction.
Let's say it's 10 to 1, which is 55. 10, 2. It's 55. It is correct, right? If your equation n to n minus 1 over 2, then therefore 10 and 10 is 9, is 45. 10 to the 1 is 55.
Professor, I think the equation should start from n, not n.
Oh, okay. Should be started from 9, then 1. 9 to 1. Okay, 45. 9. It should be 10. 10 is 55. Okay, yeah. n minus 1 is correct. Let me fix this. I will, okay. Yeah, I will upload in my notebook. It's very hard to do this in my iPad. Okay, so now we understand what is a selection sort and how we analyze a selection sort. We understand. So by looking at this code, you can draw in your brain. Okay, so this is the upper bound is n squared. Oh, wait. I can do this. Therefore, I can do some constant, which is smaller than 1, than n squared. Therefore, I can set up 2 constant. Therefore, it is etc. of n squared. Okay, so by looking at this code, you should have ability to compute n squared. Set of n squared. Okay, go to the point. Okay, insertion sort. Let's do this one as an example. You know what the insertion sort is, right? So let's do this. Let me show you the insertion sort. Insertion sort. So now we understand what is insertion sort. I'm sharing it. Okay. So some delay. Okay, so insertion sort. You know how to do this insertion sort now. So I'm keep maintaining it, this one as the index, and find the left position. So all the left side is sorted. Okay, so your index point at the barrier, and this is what you do, and you keep swapping. So this involves a while loop instead of the just for loops. So the analysis is less mechanical. But n calls in a inner loop, which takes most n steps on each call. So sometimes it is smaller than n. All agree? So I don't need to go all the way to the left, but in the middle I can end. True, right? Your while loop can be escaped out of it. Therefore, in the worst case, I can say, oh, I have to go to all the way, which is n squared with the C1. In the best case, oh, I don't need to do all the way, but a very small step. So all the way to go to left should be n to n. Then I don't need to go to all the way, then just one time, something like this. So n is very small, but therefore I can say, okay, n squared, I can make a very small n and big one. So I can have C1 and C2, meaning that I can have big set out of n squared. Clear? Okay.
Yep.
Yeah, so for example, the solar cells versus rocket. So badass rocket hits a high speed before it runs out of fuel, then cost at constant speed VR, meaning your rocket is launched from the Earth and keep getting its pace, keep getting its speed until you drain all the sources, all the fuel. Then from there you're constant. How about solar cell? Solar cell is slowly accelerate from the force of radiation and solar wind hitting it. The speed is constantly increasing. So if you look at this, the rocket is rapidly increasing, then stay there. Solar is very slow and keep catching the speed from the radiation from the solar. So we don't really care about the small number, we care about the large number. So in the end, we'll exceed the speed. Clear? So we talking about the asymptotic. This is asymptotic interaction. Okay, so asymptotic dominance, we talking about the big number, not the small number. So we want to know what's happening in the end, not the small numbers. Okay, so to prove it, I tested with the 10 and 100, and it works well. It's much faster. Then the question will be, how does it work when the input size is 1 giga? Okay, so we care about this big number, not small numbers, small points. So asymptotic notation, asymptotic dominance in action. So function of n, when the file sizes keep increasing, if your function works on log n, still maintaining it's a microsecond. Even your input is 1 billion. Okay, if your function runs in n time, then took about 1 second, even in 1 billion. When it's n log n, it's 29 seconds, but n squared, from there, 10 million is 1 day. Your algorithm cannot be useful. Your algorithm is not useful anymore. When the input is 1 billion, your computation takes 31 years. You can't use this. 2 to the power n, if your input is 50, takes 13 days. If your input is 100, very long times, not in your lifetime. Okay, it is n factorial is the worst. With the size of 20, it takes about 77 years, which is not useful. Okay, try to remember this. And we have to avoid n factorial and 2 to the power n. Especially n factorial is the worst case. Okay, so implicit implication of the dominance. Exponential algorithm gets hopeless fast, and quadratic algorithm get hopeless before 1 million. And n log n is possible to about 1 billion, and log n never gets wet. And testing the dominance. How can you test the dominance? So f of n dominates g of n. Okay, I want to test it. When there is this complete, very obvious dominance, I can say, oh, there's big O n. But if there is small differences, I want to test it. Then we call the small o notation, little o notation. So we are doing limit n to the infinite. So f of n dominates, then since f of n dominates, it rapidly increasing. Therefore, the number goes to 0. True, right? Because f of n is bigger and faster and g of n slower, therefore it will take over. Then we can say g of n is little o of n. So your little o, f of n dominates a g of n. Clear? We can also say little omega f of n, which means it is my lower bound, and this is my upper bound. Very tight. Okay, so not the little o means grow strictly slower than. So big O is something like, okay, I'm here big O. Big omega, I'm here big omega. But little o is, I can always guarantee that, even if it's tight. So it is strictly lower than this. This, then I can strictly note on this. Okay, so we can test with this infinite. So property of the dominance. So n to the power n dominates n to the power b if a and b, a is bigger than b. So let's say this is fn and c of n. So I can put it, my notation. This goes to b minus a. A is always bigger, therefore it goes to a very small number. That in the end, it goes to 0. Clear? So something like, if a is positive, a is bigger and b is smaller, then it is n to the 3, something like this, n to the 10 over this. This minus become something like this, right? Then in the end, it will goes to 0. How about second one? N to the power a, little o of n to the power a doesn't dominate n to the power a. Let's put it our equation. So n to the a, little o of this one. Oh, what we care about is the dominance one. So definitely this is bigger than this one. Then I can ignore this. Then it's constant of this one, it goes to the 1. So it's not dominant. Okay? All right, so dominance ranking. So you must come to accept the dominance ranking of the basic functions. So n factorial is the worst, then sequentially, it is on the right side is better. If it is constant time, oh, I can do it in right away, right? Log n, it takes some time, but it's very tight. If you have more advanced dominance ranking, so additional functions arise in a more sophisticated analysis than we'll do in this course. So n factorial to the n. So in between, we put it something. So we can put more on this. Then what we care about whole this semester is up to this point. Okay. All right, so logarithm, what is logarithm? Logarithm is about the halving it, and exponential is a doubling it. Okay, so it is important to understand that deep in your bone what logarithms are, where they come from. A logarithm is simply an inverse of the exponential function, saying b to the x equal to y is equivalent to x is log by. Okay, logarithm reflect how many times can we double something until we get to n, halving it something until we get 1. So remember, doubling and halving it. Why is it important? Do you know binary search tree or binary tree? What is so powerful in the binary tree? So go to there. I can make a decision. Oh, I'm going to this way, meaning I can ignore half of it. Then from here, I choose this way, meaning I can ignore the half of it. Okay, you will keep ignoring halving it. You keep ignore the half of it, meaning your computation load will reduce dramatically. Halving and halving, halving, keep halving it. Okay, that's the power of logarithm. So binary search. In the binary search, we throw away half the possible number of keys after each comparison. So does 20 comparisons sufficient to find the name in the billion name in sold phone book? It is true. And how many times can we halve n before the to 1? Let's do this. How do you find your name in a phone book? We don't have yellow book these days, but a long time ago. Let's say I'm looking for a dictionary. How can you open it? If it is before or after, you go to that, you halving it again, and go to left and right. With the 20 times of it, and you can find the exact number what you are targeting. That's the power of the binary search. Okay, how many times can we halve n before getting 1? So I want to, let's say this 16. How many times can we halving it? 16, I can halving it 8, I can halving it 4, I can halving it 2, I can halving it 1. Ah, okay. If it is 32, I can halving it 16, 8, 4, 2, 1. What if it is 33? Oh, I can halving it 16 and 17, right? Then from here, I can take this guy. What if it is 25? I can halving it 16 and 9. From here, I can halving it 8, 4, 2, 1. It is 4 and 5. Let's say 5 and 4. I can halving it 2, 1. 5 is 3 and 2. 2 and 1. 2 is 1. Something like this. Okay. So how many times can we halving n before getting 1? Who knows the answer?
What again?
So how many times can we halve n before getting 1?
Log 2n.
Log 2n plus 1.
Y plus 1. Y plus 1?
In the case of 16, like we have 1 left. 16, 8, 4, 2, 1. The halving process itself will be log 2n.
Yeah, so halving process is n, right? Getting to 1. Good point, thank you. So log n, right? So log n at best. So let's do logarithm and trees. How tall a binary tree do we need until we have n leaves? The number of potential leaves are double with each level. So 1 become 2, 2 become 4, 4 become 8. You will keep doubling it. How many times do I have to grow from here to there until to get 1 n? 1 to n. How long does it take?
Log 2n.
Log 2n.
Plus 1.
Okay.
Yep. Y plus 1.
We have to count the origin.
Okay, so okay, log 2n plus 1 or log 2 is dominant is log n, so doubling it until, so from 1 to n, so log n. So I'm assuming you understand the concept of log, and you are now have ability to play with it in the algorithm, conceptually. Okay, so how logarithm and the bits. So how many bits do we need to represent the 0 to this guy? So 0 to, let's say it is 15. I should have 0 to 15. How many bits do I need?
4.
4. 0 to 3. How many bits do I need?
2.
You understand what it is, everybody?
Yes.
Yeah, so
Yes.
0, 0, 1, 1, 0, 1, 1. Then I can represent 0, 2, 3. 0, 0, 0, 1, 1, 1. I can represent 0, 2, 7. Clear? So each bit you are adding double the possibility, double the bit pattern. So the number equals to log to I is I. Okay? So logarithm and multiplication. So recall that log xy is dividable to individual. So this is how people used to multiply before calculators and remained useful for analysis. Now we understand this, right? Can I assume everybody understand this? So what if x is a? What's the result?
Just 1.
Yeah, 1 plus log ay, right? 1 plus log ay. So now you have ability x and x is dividable and it ends up with the 1. Okay. So base is not that important in the asymptotically. Why? Because we don't see in detail, but roughly saying, okay, in a big number. That's the power of asymptotic. So I'm sure you know about this. This is equal to x, right? And this one is divided to this one. So thus, log to n is same as this one. So if you divide this one as a constant, it is about 6.63, which is just constant. So it doesn't matter in the big O notation. Okay, so we care about the big O notation and the big number, and which is dominant. We don't really care about the minor details of it. Okay, one question. Okay, say you are the thief. What is a better way to do a thief? What do you mean? What do I mean? So let's say this is the sentence rule of the judge, and 2F1.1. This is guideline for the fraud and deceit and forgery offensive involving a third or counterfeit instrument other than counterfeit bearer obligation of the U.S. So base offense is 6. You are meaning you have to pay if you are a thief more than $70,000. Your sentence will be added six more years. Okay. For example, if you lost exceeded 2,000, lost exceed 2,000, the following offense is 1 year. Okay. So if you try to steal the supercar, you have to I category, then you'll go to jail for 8 years. Okay. If you try to steal the MacBook, then you are category B, and you have to go to the 1 year in the jail. Okay, look at this. This is logarithm. Do you see? So let's say I am a thief with the 10 times of 10 MacBook. How long do I have to say? I have to spend 10 years in the jail because I did 10 times of the $2,000 plus. Okay. What if I stole the, this is cost at the $20,000, you spend 10 years in the jail. But what if you try to steal the Benz, Mercedes-Benz? Let's say Benz is about $100,000. Then you are going to jail for 6 years. 6 years to $100,000. See, you stole $20,000, spent 10 years, but you stole $100,000 and spent 6 years. Which one do you prefer?
If
you want to be bigger thief, right?
Yeah.
So when
if we
you
steal,
try to
we
make
steal back.
Yeah. Okay. So make the crime worth the time. So this increased the punishment level logarithmically in the amount of money stolen. So they pay us to commit one big crime rather than many small crimes. Okay, if you want to be a thief, try to make a big one. Okay, small one doesn't count. It just wastes your time. All right, so even our daily life and law and the base of the system works in a logarithm. Okay, so this is what I prepared today. So midnight tonight is the PP1 due date, and try to submit it on time. The PP is not designed to be challenging you, but designed to help in your understanding. It'll be easy, but can you hear my voice?
Yes.
Yes.
Okay, how about now?
Great.
Yes.
Awesome.
So PP is designed to help you understanding. Okay, not designed to challenging you. So it will be easy, but after practicing it, you understand the topic, you understand the subject much better. That's why I give you easy questions as a program practice, and I want you to practice what we learned in the class. Okay? All right, any comment about the class?
Nope.
Okay, so I'm encouraging you to participate more actively, and if you have a question about the homework or anything on the class, please comment on the Google Classroom. Then everybody share your comment.
Yes, sir.
All right. Anything else?
Thank you.
All right. So thanks for coming today, and see you on Wednesday.
Yeah, Professor.
All right.
Thank you.
Thank you.